Good evening, everyone. My name is Samir Kumar Singh. I am PhD scholar, and today we will discuss the week 3 tutorial. So, hello, hello, Akila. Can you hear me? Hello, hello, Akila. Okay, okay. Can you hear me? Screen is visible. Okay, okay. So we can start. Okay, we can, so so today we will discuss the week 3 tutorial. Okay, and this may help you to solve the questions of the week 3. Okay. So Akila, question number 1 is on your screen. Okay. Maybe few students joined after few times. So question number 1 is, we have a message signal empty, okay, and modulate a carrier with CT where FC is given 1 megahertz, and there we are producing an AM signal. Now for the demodulating the generated AM signal using an envelope detector, the time constant RC for the detector circuit should satisfy. So we have to calculate that RC value of RC, that is time constant. So please try, and after 2 minutes we will discuss the solution and the steps. Question is clear? अगला question is clear? Okay, please try. After a few times we will see the solution and steps. So there we will calculate the time constant. Hello Minaz, good evening, good evening. Question number 1 is on your screen. Okay, please read this and try to solve this. And after a few times we will see the solution. Okay, again I am repeating the question. Question is, a message signal empty, and we are doing the modulation with the carrier signal CT, that is given cos 2 pi FCT, where FC is 1 megahertz, and we are producing an AM signal. Now we are doing a demodulation. So for demodulating the generated AM signal using an envelope detector, the time constant RC of the detector circuit should satisfy. So there we have to calculate the time constant. Yeah. Okay, we will wait for 2 minutes. With, I think Akila is solving. Hello Pranali. Okay, I think. Okay, that this is the question number one. Actually, we have to calculate the RC, time constant. We have an MT and we have a CT. So we are doing the demodulation by using the envelope detector. Okay, now we will go over the solution. Right answer is B part. Okay, and that is the steps. Okay, so first of all, our MT is given cos 200 pi 2000 pi t and 4 cos 4000 pi t. It's a combination of two measure signal. Okay, we have a carrier frequency 1 megahertz. So first of all, we will calculate the FM of the message signal. So for the first term, our FM will come 1k because we divide this 2000 pi by 2 pi. So from there we will get FM1, that is 1k, and from there we will get 2k. So we will consider the maximum frequency. So the maximum frequency of the max signal will be 2 kilohertz. That is clear. Okay. So now we have a carrier frequency 1 megahertz and the message signal frequency of message signal is 2 kilohertz. Okay. So from there we can calculate the time period of the message signal and time period of the carrier signal. So Tm is equal to 1 by Fm. From there we will get the time period of the message signal. It will come 0.5 milliseconds. Similarly, we can calculate the time period for the carrier signal. Tc is equal to 1 upon Fc and it will become 1 microsecond. So when we do the demodulation by the using the envelope detector, so there is a one criteria, and so that is the proper operation of the envelope detector time constant. RC should be lie between the TC and TM. Okay, so RC should be lie between the TC and TM. TC is 1 microsecond and TM is the 0.5 microsecond, and the answer will be B part. Question is clear? If anyone have doubt, please ask. No problem. What, ma'am? Ma'am, it's for the week three. Week three. It's helped. That a question of will help to solve the assignment number three. Uh, three. Solution is clear. Okay. So it's a general signal and it's envelope. You can take as a short notes. If we have a VM cos 2 pi FMT, so generally we consider the magnitude. So for this, its envelope will become VM. Similarly, if we have ET cos t, so for that we consider the e to power minus t as an envelope. That is a direct formulas. If we have a cos 2 pi f naught t plus v cos 2 f naught t, so you can take the square root of the a and v. Okay. Now question number two is on your screen, and please try. We will discuss the solution of question 2 after 2 minutes. The question is, consider the amplitude modulated AM signal AC cos omega ct plus 2 cos omega t into cos omega ct. For demodulating the signal using envelope detector, the minimum value of the AC should be. Again, we are doing the demodulation by using the envelope detector. So there we have to find the minimum value of AC. Please try. Vinaj, question is clear? Okay. 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 We will wait. Ma'am, you got the answer? Okay, okay, no problem. Okay. Now we will go for a solution. Okay. So answer will be a part, and that is a solution. Okay. Basically, we have an AM signal, and that is given that AC cos omega CT plus 2 cos omega MT cos omega CT. Basically, this is the general. Generally, we write the AM signal in this form. So, actually, equation of the AM signal we will represent on this form: AC cos omega CT 1 plus MA, that is modulation index. We can also call this mu into cos omega mt. So we will try to make the equation 1 as a equation number 2. Okay, so there we take the common, the AC cos omega ct, so it's become 1 plus 2 upon AC into cos omega mt. That is clear. Now we will compare the equation number 2 with the equation number 3. From there we got our modulation index is equal to 2 upon AC. Anyone have doubt from on this step? Okay, so now we are doing the demodulation for the proper annual direction. Our mu, or we can say modulation index, should be equal to or less than the 1. So we can write this term on 2 upon AC is less than 2, less than equal to the 1. Okay, so sorry. So from there we will get AC greater. Sorry. Okay, so we'll get AC greater than equal to 2. So minimum value of AC from there we will get is equal to 2. Solution is clear? Okay, so option A is the right. Okay, now question number 3. Try this. We have a modulated signal, that is ST, is equal to M1T cos 2 pi FMT plus M2 sin 2 pi FCT, where the bandwidth baseband signal M1T and M2T have a bandwidth of 10 kilohertz and 15 kilohertz. So we have to calculate the bandwidth of the modulated signal in the kilohertz. Here we have to calculate the bandwidth of the modulated signal. It would be a FM, not FC. Okay. Question is clear? Okay, after 1 minute we will go for the solution. Till then you can try. Okay, so answer will be D part, and now we'll see how can we get calculate the bandwidth. Okay, so we have a message signal, that is a M1T cos 2 pi FCT plus M2T sin 2 pi FCT. So we have to calculate the bandwidth. Our general formula of the getting the bandwidth is F equal to 2FM. So we will try to find out the uh, message frequency of the message signal. Generally, we have two component, MT cos 2 pi FCT and MT M22 sin 2 pi FCT. So overall, our maximum frequency is equal to max of the FM1 and max of the FM2. So there FM1 is given 10 kilohertz and FM2 is given 15 kilohertz. So there we will pick the maximum value of FM. So from there we will get our FM is equal to the 15 kilohertz. we will put there. From there we can get our bandwidth. So bandwidth is equal to 2 times of FM, and it will become 30 kilowatts. That is clear? Okay. Okay. So that's the question number 4. Please calculate find the Hilbert transform of the cos omega 1t plus sin omega 1t. Please try. Question is clear now? Okay, okay. Inaj, you got the answer? Okay, no problem. Akila? Akila, ma'am, are you trying? Okay. Okay, okay. Sorry, it would be omega 2, not 1. Cos omega 1t plus sin omega 2t. Okay. Okay, we will go for the solution. Okay, the answer is A part. Okay, and that is the explanation. Actually, in the Hilbert transform, we will do the shifting of the 90-degree in our given signal. So xt is given cos omega 1t plus sin omega 2t. So we generally shift all the given signal. That is the notation x hat t. So there we did a shifting of the minus 90-degree in first term. Similarly, we did a 90-degree shifting in sine in second term. Next, we did the just rearrangement. As we know, cos minus theta is equal to cos theta. So we can write cos omega 1t minus 90 degrees equal to cos 90 minus omega 1t. But in the case of sine 90 minus theta, minus will come out, minus sine theta. So we can write this term cos 90 minus theta become sine theta. So cos 90 minus omega 1t become sine omega 1t. Similarly, sine 90 minus omega 2t become cos omega 2t. So that will be answer. Steps are clear. Okay, please ask. What about negative? Okay. Yeah, generally we did a phase shift of the 90 degree. Yes. Okay, you are talking about the frequency, but there we are talking about just about the phase. Okay. 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 Question number 5 is given, and question number 5 is the unmodulated carrier power in. Hello. Okay. Question is the unmodulated carrier power in AM transmitter is 5 kilowatt. That is AM. The carrier is modulated by a sinusoidal modulating signal. The maximum percentage of the modulation is 50%. It means mu is 0.5. If it is reduced to 40%, then the maximum unmodulated carrier power that can be used without overloading the transmitter is. So there we have to calculate the AC, maximum unmodulated carrier power. Sorry, power of the AC. So try this. Question is clear? Okay, actually, question given it. I will start from this initial. Okay, the unmodulated carrier power in AM transmitter is 5 kilowatt. Okay, before modulation. We have 5 kilowatt. Next, the carrier is modulated by a sinusoidal modulating signal. Here the maximum percentage of modulation is 50%. Okay, so we can do the modulation. We can consider the mu is 0.5. If it reduced to 40%, now we are reducing. So find the maximum unmodulated carrier power. The significance of the overloading is just like a overmodulation. Okay, generally as you know PT is equal to PC 1 plus mu square by 2 na. Basically we Okay. So here PT is constant. Okay. In first case, that is given a 5 kilowatt, and modulation index is given. So from there we calculate the power of the massive signal. Okay. And now that PM we will use there. From there we will get our power of the carrier signal. I think you got. So first of all, okay, we will go for solution. Okay, so answer will be V part, and how it's come we will see there. Okay, so firstly, given is our carrier power is 5 kilowatt, modulation index is given 5.5, 50%, and for the second case it's become 0.4. So from first case we will got PT. Okay, PT is equal to PC 1 plus mu n square by 2. From there we got out PT is 5.625 kilowatt, and now we will uh, 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 now we will use this power for the second case, and we will try to get a modulation index mu 2. Sorry, I mean PC. Mu 2 is given, PT is given. From there we can get our PC. It's clear? Okay. So can we go for next question? Okay. So that is the question number 6. Question number 6 is the amplitude of a sinusoidal carrier is modulated by single sinusoidal to obtain the amplitude modulated signal ST. Okay, find the value of the modulation index. There we have a sinusoidal modulated signal, sorry, AM modulated signal, and there we have to calculate the modulation index. So please try. As a hint, you can write the basic expression of the AM signal. From there you can get, you can calculate the modulation index. Question is clear? Okay. 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 Uh, Answer will be C part, and that is explanation of the question. Actually, we have given the ST, that is a modulated signal, AM modulated signal. Okay. So as we know, standard expression of the AM signal. Okay, when you open the expression of the AM signal, you will find, you can write the expression on that form. So there we will try to rearrange accordingly. So basic, okay. So from there, yeah, we consider the higher carrier frequency at the 1800 pi t, 1800, because that is FC, or our FM will be 200. The FC minus FM becomes 1600, and FC plus FM become 2000. So from both, we can compare both these equations. So from there we getting the our AC is equal to 20, and AC mu A upon 2 is equal to 5. Mu is the modulation index. AC is given 20. Just put there, and from there we can get the modulation index, that is the 0.5. It's clear? Or if anyone end up doubt, please ask. Can we go for next question? Okay. If anyone have a doubt, please ask. Okay. Okay. Question number 7. And question number 7 is, consider sinusoidal modulation in an AM system, assuming no over modulation. The modulation index when the maximum and minimum value of the annual respectively are 3 volt and 1 volt. So find the modulation index. So please try. Questions clear? Okay. Minaj, you got the answer? Anyone? Got? Okay. Okay. So answer will be C part, and how it's coming we can see there. Actually we have an envelope, okay, and the maximum value is given a 3 volt and the minimum value is given the 1 volt. Okay, so now we have to calculate the modulation index, and that is a general formula. Sorry, it will be E max minus E min, and it will be upon E max plus E min, so it will be plus. Okay, so from there you just put the value 3 minus 1 upon 3 plus 1, and it will become 0.5. Okay, I will try. Okay, Actually, when we are doing the demodulation, yeah, I mean, okay, yeah, okay, yeah, there we are talking about the no over modulation, na? So we are trying to avoid the over modulation. Okay, so sub, yeah, okay. So here we plotted the, okay. So yeah, there we plotted the envelope. Okay. So according to that envelope, they are saying we have the maximum value is a 3 volt. Okay. Suppose you have a sinusoidal signal and you are plotting the envelope. How it will come? Yeah, you did the just M modulation. When you plot the envelope, okay, so it will lies a few max value. I mean between the live maximum value and minimum value. Okay, be okay. So that is given the three and one. Well, I mean, it's lying above the axis. Just assume we have a two axis, x axis and y axis. Okay, and on the in the y axis, our envelope is lying between the 3 volt and 3 volt and 1 volt. Okay, so from there, we have to avoid the over modulation. Huh? So uh, from there, we are getting that formula, and it will be plus and will be 0.5. If you are not, otherwise, I will explain this concept in the next class. Okay, if it's not clear by making the pictures and some. Okay, okay. We will discuss. I will discuss this point on the next class. Okay, with I will come with the proper figure and proper. Okay, because I have no writing pad right now. Okay, okay, okay. Question number 8 that is given. Consider a signal PT that is equal to 1, that is lying between the minus t by 2 plus t by 2 and 0 otherwise. Its autocorrelation is, you can plot a PT. It will be a rect pulse from minus t to t by 2 plus t by 2. Okay, and there we have to calculate the autocorrelations. So if question is clear, try to solve it. Okay, we will wait for others response. Please participate. If you have doubt, please ask. Question is clear? Akila? Archana? Akila ma'am? Archana ma'am? Okay, please participate. Okay. Okay, we will go for solution. No, no, please try. I think you're not confirm. I will check. Option is the A part is the right answer. Okay. Okay. Answer is the A part. Okay. And that is a solution. Actually, PT is given 1, and that is line from the minus t by 2 to t by 2. Actually, basically, it's a rect pulse, and 0 otherwise. So we have to find the autocorrelation, and we can, to get the autocorrelation, we convert the PT with the PT star minus t, and their function is even function. So we can write the that term in this form. It will come PTT. Okay. So rest, so mainly there we are convolving the two rect pulse. Okay, that is lying from the minus t by 2 to plus t by 2 and having a amplitude 1. We have to convolve the two rect pulse that which are similar. And that case we will get the output mod t minus capital T minus small t. Okay, basically the convolution of the two rectangular pulses, height 1 and width t. We have a two input signal, I mean PT signal is that having a height 1 and width t. When we did the convolution of that rect pulse, we will get a triangular pulse with the height t and with the capital 2T. Okay, don't worry that there is explanation. Okay, so there we consider the two rect pulse. Okay, which having the amplitude A, the magnitude from minus t to capital T. Okay, suppose that is ft and that is a gt, both are the same, and we are doing the convolution. Just to do the integration. Okay, so when you will go for that, you will get that result. Okay, so from there we get the result. It is a general equations. From by using this concept we can convert any two rectangles. So there we are getting the amplitude, it's mod capital T minus small t. Answer will be A part. Okay. Okay, question number 9. Question is, consider the AM signal with power efficiency 1 by 9 and total power is 1. The expression of the AM signal is, we have a power efficiency eta and total power is given 1. So just find the A and K, other thing is given there. By getting the A and K, we can write the expression of the AM signal. So try this question. Question 9 is clear? Okay, basically we have a power efficiency is given and total power is given. So by using the eta, you can calculate a modulation index, and then by using total power is given, from there you can get the amplitudes. So please try. I hope you all will solve this question. Okay. Uh, anyone other than Miraj, Minaz? Anyone got the answer? Question number 9 is given. Okay, actually power efficiency is given. From there we can get the modulation index K. By using the modulation index and total power, we can get the A. We can calculate the value of A. Okay, so answer will be B part. So please focus there. That is the solution. Actually, the RM signal is given in this form, and power efficiency is given 1 upon 9. Okay, as we know, power efficiency is equal to mu square, or we can say K square upon 2 plus K square. By using this formula, we can calculate the power efficiency, and that is given 1 by 9. To use our simple mathematics, from there we can get the value of K, and that will become 1 by 2. Okay, so we got our modulation index, or we got the K, that is 1 by 2. Now given is that total power is 1. Okay, so as we know, PT is equal to PC bracket 1 plus mu square by 2, or we can say 1 plus K square by 2. When we open, you can write PT is equal to, and that is given to equal to the 1. Just put the value of K, and from there you will get the value of A. So K is 1 by 2, capital A is 4 by 3. Just put the both values in this equation. So that is the answer. It's clear? Okay. Okay. Now question number 10. Question 10 is, consider signal xt. Its autocorrelation defined as. Again we have to calculate autocorrelation, and that is the formula is given. Just put these values, change the limit, or let me know the answer. Question is clear? Okay. You solve the answer, yeah, or you know the answer. Okay. Okay. Good, good, yeah, good. Okay. Just put the values. Actually, UT is given, so limit will be good. Good, good, good. Yeah.
Okay. Okay. Okay.
Okay, good. Thank you. Okay, there. Okay. Okay, thank you. Yeah. Mhm. Okay. So now we will go for the solution. Okay. Answer will be C part. So just xt is given e to power minus 80 into ut. Just put the values due to ut. It's will be lie from 0 to infinity. It's become e to power minus 80, and it will be e to power minus 80 t minus tau. Okay, when you apply the integration, you will get the that part. Okay, so next question is on your screen. Question number 11 is it's a theoretical question. Already we solved the question number 1 or 2 that based on the same concept. Okay, question is consider the envelope detector with the load resistance RL and capacitance C employed to detect an AM signal with a carrier frequency FC and a message frequency FM. It's desirable that again we have to calculate a time constant, that is RLC. So which one is the okay? Question number 1 and 2 is same. There we are doing the numerical. Uh, okay. So tell me which is a desirable, which option is correct? Okay, answer will be a part. As we know, our time constant or RLC should be lie between the range of 1 upon FC to 1 upon FM. Okay, so that is the explanation for the envelope detection. It is desirable that our RLC should be less than the 1 upon F. So because the rate of discharge of the capacitor is faster than the rate of the charge of the message signal, so that output tracks the message signal. Yeah. Next is the question number 12. Consider an ordinary amplitude modulated signal with the modulation index mu and a sinusoidal message signal. The power efficiency of the signal is. Okay. Anyone else? Okay, sir. Right. Okay. Basically, there is given the sinusoidal message signal. Now, I'm giving you homework. Suppose our message signal is not a sinusoidal. Okay, and we are considering other type of signals. So on that case, our power efficiency will be same or it will be changed. Sure. Try to find it. Okay. We will discuss on that point. I'm saying that here we are considering the sinusoidal message signal. Okay. On that case, we are getting our sure. Okay. Okay. Think about that. We will discuss on that topic on next class. Okay. Consider the other type of message signal. Okay. There is sinusoidal, and next we consider various type of message. Suppose we have a rector. I mean, we will discuss it on next class. Okay. Please think about this. Okay. For the sinusoidal, our efficiency will become mu square upon 2 plus mu square, right? Mu square. Okay. So, so that is the just explanation. We have a given an ordinary amplitude modulated signal with a modulation index mu and a sinusoidal message signal. The power efficiency of the signal is mu square upon 2 plus mu square. Okay. Okay. That is the question number 13. Question is consider a AM signal with the power efficiency 1 by 19 and total power is 19 by 9. The expression of the AM signal. Please try. I think question number 7 or 8 same, just like a same. So using the same concept, try to find the value of A and K. We have a power efficiency 1 by 19. So from there we can calculate a K. Okay, please try. Okay, we will see later. Anyone else got the answer? Okay, answer is A way. Okay, so what's up? Anyone's saying? Okay, answer will be A part. Okay, that is the explanation. We have power efficiency, and we know the formula of the power efficiency for the sinusoidal massive signal. That is mu square upon 2 plus mu square, or k square upon 2 plus k square. From there we can calculate the modulation index. That is the mathematics, and it will become 1 by 3. And given the total power is 19 by 9, so by using this we can calculate the A. That will become 2. So just put the value of the A and K. It become, so A part is the right answer. Okay, that was the last question. Next, I want to know. I added a few MATLAB how we can generate the sinusoidal signal in the MATLAB. Okay, so now we'll go for that session. My screen is visible. Huh? Okay, if you know, then it's good. Otherwise, just look at on the screen. So there I consider two code how we can generate the sine signal on the MATLAB. Okay. Okay, everyone can see my screen. It's visible. Okay. So our objective is okay. So there our objective is to generate the science science signal in on the MATLAB. Okay. So in the basically we in MATLAB we use the three basic command. Okay, that is the CLC, close all, and clear all. Okay, the actually we have a uh, as you see there we have an editor, workspace, and command window. So we use the CLC function to clear the command window. As you see there, yeah, here we lots of term in the command window. If you want to clear it, just type the CLC. So CLC clear your command window. Okay, and next we declare the close all. Basically, close the all figures. Suppose you run the code. Okay, okay, but we want to close it. Close the previous figures. Type the close all. Okay, it will be close the previous figures. And similarly, we use a clear all that clear the workspace. As you see there, we have a few variables. Whatever we declared at t, u1, u2, and it shows the what value t have what's the value at t having, like you can see there in the t. In t we have a 401 values. Okay, so to clear the workspace we using the clear all. When you type the clear all in on a command window, our workspace will be clear. These three is clear. Basically that these three are the initial commands. Hello everyone, it's clear. Please respond. Okay. Okay, now we have to generate the sign signal now. So hello, yeah ma'am. Akila, you want to say something? Okay. Okay, so we have to generate the sine pulse, sine signal in on the MATLAB. So basically if we plot on the two axis, x axis and y axis. So basically हाँ या मैम बोलिए. Yeah ma'am. Yeah Akila, please speak. You have any doubt? Okay, 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 no problem. Okay, no problem. I'm saying that you have any doubt? Okay, so there our motive is to generate the sine pulse, sine signal. So actually, when we plot when there we are plotting a sine signal. So if we plot on a two axis, x-axis and y-axis. So if we actually whenever we plot the sine signal, we plot it on it with respect to time. So see there we declare the time interval that is mentioned by the t from 0 to 0.1 with a gap of 0.001. Okay, so please tell me how many value will t contain. We have a 0, 0.001. Next we have a 0.002. Okay, we will plot our sine signal on that interval. Next we will see how many value, how number of values our t has containing. Next we declare that our amplitude towards the, yeah, okay. Whenever, yeah, we are taking the value from the 0 to 0.1 with the gap of a 0.001. Okay, okay, yeah, okay, okay, okay. Next we consider our amplitude of the sine signal is 10. Okay, next is the phase shift. We consider the pi by 2. Okay, so now we write over the sine signal. Actually general equation of the sine signal is am sine 2 pi fmt. Okay, so that is the a declare a denote the, okay, okay, ask. No, no, it just a variable. It's just a variable. Ph is a variable. Pi have a standard. Okay, that is. But pH is the just a variable. Okay. Sine. Okay. That having the, okay, okay. So there we have a V1. Okay. V1 is equal to a sine 2 pi fmt. We consider the frequency 30. Okay. Next we want to shift the sine pulse by the phase shift of pi by 2. We write there. There we added the phase also. Okay. Now our task is how we can plot on the MATLAB. Okay. There we are plotting the two function. First one the V1 and second is the V2. Okay. So to draw the if you want to draw the multiple plot in one screen, so we are using the subplot. Okay, suppose whenever you write the subplot xyz in MATLAB, so x represent the row, y represent the column, and z represent the plot number. Actually there we as or there we are plotting the two, there we are draw the two plots, p1 and p2. So that is a plot number. Okay, so now we will run this code. Okay, that is okay. So there we plotted a sine pulse in the continuous domain. Okay, next we plot the sine pulse in the discrete domain. How we can draw the in discrete domain? We will go for the view again. Okay, we use the plot for the plot to draw the continuous signal, and we use the stem function to draw the sine pulse in the discrete domain. Okay, if you want to draw in a discrete domain, use the stem. T represent the x-axis, and v1 is the our sinusoidal signal. Ha, plot, subplot, stem, that is the standard function of the MATLAB. Okay, so uh, there we plotted our v1. Okay, please sir. Okay, okay, one is the plot number. Last one is the plot number. Last one is the plot number. Okay, actually there we overall we plotted a four plot. Okay, you look at there. Okay, that is the plot number one. Yeah, so that is a continuum. Okay, to any, if you draw in a discrete domain, just use the stem function. Okay, and that is the and v3 denote okay, that is the shifted sine pulse. Okay, v2, that is a plot of the v2 in continuous domain, and that is the v2 in discrete domain. It's clear? If anyone have a doubt, please ask. It's a journal MATLAB code to generate the sinusoidal signal in MATLAB. Maybe it help you. Okay. Similarly, we plotted the cos pulse. Nothing is new there. Just we replace the sine with the cos. Okay. That is also a standard function. Okay. So that is a curve. That is the result. That cosine pulse in the continuous domain. That is the discrete domain, and that is shifted cosine pulse. Okay. So I mentioned all the code and result on the PPT slide. Okay. So that's from my side. Today's class is over. If you have any doubt, yeah, any suggestion, you can say. I will try to improve it on next class. Yeah, yeah, yeah. Okay. I just need you all's feedback. MATLAB session is good, or we can remove it, and we can add more questions, or we can add more, or we can go for the MATLAB session as you guys decide. Okay, 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 okay,
Okay, okay.
it's okay, okay, okay. Kirti, Akila, Gali, I also need your feedbacks. I mean, I need your feedback about this class. How, what you want, and how much it's helpful for you. No problem.
Okay.
Okay. Okay. Okay. Okay. You can. Okay. If you are having any conceptual doubt, you can post there. I think on the portal, we all will try to give your answer to resolve your queries. Okay, MATLAB. Yeah. Okay. 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 I will try. We can discuss on the concept. Okay. But okay, we will try. We can try. Okay. Okay. So I think it's over. So can I cut the class? Okay. Thank you. Thank you for joining. Okay. Okay.